So welcome everyone. It's great to see you. Even those of you who don't have your cameras on, we can imagine you, and we're really glad to have you with us tonight for our, I think this is the third To Serve with Love talk with our guest tonight, which is Dr. Phil Marshall, and we're going to let Phil introduce himself in just a moment. But we're really glad to have you here with us, and thanks for spending an hour tonight as we gather in community. And I was telling Phil before that I wanted to do this very short little reading to kind of set the tone for tonight. So I subscribe to a magazine called Image Magazine, and the purpose of Image Magazine is the exploration of art, faith, and mystery. And it has a lot of amazing people who I get to get introduced to in this magazine. And so this was an essay by a professor of literature in New York talking about a writer who I had never heard of before, Catherine Davis, who he puts in a grouping with Annie Dillard and Marilyn Robinson, which many of you know, under a genre which I never knew had a name, called cosmic realism. Get it there, Phil? Cosmic realism. So now you understand why I was so curious about this. So he talks about cosmic realism as these two writers particularly, and Catherine Davis as well, who are very interested in what it means to literally be in time. This whole idea of like the experience of who we are, this individual moment, this being in time. And so this little quote comes from a book she wrote in 1998. The title of the book is Hell. And here's the little portion that I'm going to read. It's a paragraph from the book. In the beginning, we're told, everything was the same. Everything was locked together inside a huge lump of ice. But soon enough, the ice began to melt. And because it was too huge to notice the moistly fraying hem of itself, threads of milky silt-filled water unraveled across the landscape, slowly at first, then faster, setting the miller's wheel in motion, thundering toward a future where a little yellow leaf was sweeping over the lip of a dam. Rain was falling from the sky, that spectral shade of gray that's almost white, dispiriting. And I was sitting on my father's bedside, eating fries out of a paper bag. And so Phil, have our imaginary French fries, and we're here to listen to you. We are, for those of us who are Olympic sports watchers, we are choosing physics over figure skating, because that's how much we love hearing what you have to say about the universe. And we are going to welcome Catherine McGrath in, and we'll just get her in to say hi. Hi, Catherine. Welcome. We're going to get started. And so for our third To Serve with Love, I'm going to ask our guest, Phil Marshall, to introduce yourself and talk a little bit briefly about your connection and what you do professionally.
All right, thanks very much, Alyson. Thanks to all the rest of you for taking the time to spend the evening with me. It's really nice doing these talks in the evening, because I feel like I'm visiting everybody in their living rooms at once. It's a nice thing to do. I've done a few public talks like this. It's kind of fun to look out over, 30 or 40 different living rooms. Everybody come to listen to the universe. So my name's Phil Marshall. I think I know most people on the call, but of course others will be watching and haven't seen me before. And lots of you haven't seen me for a while, because I've been busy down in Half Moon Bay, here where we live, with raising a toddler and coping with the pandemic and so on. We only just recently made it back up to San Francisco to come and attend church on Sunday mornings, and so hopefully you'll see us up there soon. We, of course, is Melinda, my wife, and Jimmy, my young son, and so you'll see the three of us around. I've been a member of UUSF since 2013, when I moved back to California for the possibly final time. And the previous 3 years before that, I was in Oxford doing a research fellowship. And that experience of moving from California, where I had been before, to Oxford, got me thinking about, how do you best find a good community when you move to somewhere new, as I had done several times at that point. And I got interested in churches and the good that they can do for the local community. I just wanted a church where no one was going to hand me a card on the way in with what I had to believe. So when I found Unitarian Universalism and the lovely congregation at San Francisco, it was really a pleasure to come and join in properly when I got there in 2013. So I've been a member there ever since. I've been contributing to services and so on whenever I get the opportunity. And it's really a good place to be and think and experience the world with a group of like-minded, interesting people. I guess that's really how I'd summarize my connection. I've done a few of these talks actually at UU, mostly with slides, standing in the MLK room, and it's kind of nice to do this just in conversation, Alyson, just back and forth, something different, something new.
And just for those who don't know, Phil, briefly, if you could just say, how do you spend your days? Where are you? Where do you spend your time? Yeah,
that's right. Part. Yes, that part. I'm an astrophysicist, which means that I study the universe and its contents, try and figure out how things work out there in outer space. That's the astrophysics part. Astronomy is sort of observing the night sky and making measurements and so on, and getting a little bit into the how things work. I like to say I do astrophysics because it's the how things work part that is one of the things that interests me most.
And where do you do this?
I do that at SLAC National Accelerator Laboratory, one of your local national labs, down at Stanford University on the peninsula. So we live in Half Moon Bay, but I commute over the hill to Menlo Park to go to SLAC for work.
Great, thank you. So just for everyone here, we have a set of questions that Vanessa and I have been sort of organizing. So there's, for those of you who've been to the other talks, you may hear questions that sound the same, but they're particular for the person who's responding, our guest, to answer them based on their experience with those. There will be a time, about 10 minutes for Q&A. So if there's a burning question you've been wanting to ask an astrophysicist, this is your lucky day. And we'll get to that at around 7:40. And then we have a couple of closing questions that we'll get to. So Phil has prepared, and I'm going to begin with our first question, Phil, because it is the month of love. And so I'm going to ask you, what made you fall in love with physics and astronomy?
So I like this question because it's a variant on one of my favorite questions, which is to do with identifying the point in time when something happened. It's like the critical point where things change from the before to the after, and we're never the same again. And falling in love is like that, right? That there's a point where with hindsight you can say, oh yes, that's the point at which I fell in love. That's when I knew, that's when I knew what I was about. I was connected in that way. So for me, looking back, I think that point was in an examination hall at my secondary school in the UK in the summer of 1994. So I was 16, and I was doing an exam called AO level maths. Not math, but maths in England. And there were only about 20 of us or so in the gymnasium doing this exam. It was a sunny day and the sun streaming through the windows. And I was doing this, exam paper. I had my graph paper to do the answers on, and I had my script where the exam was set. And AO level was interesting because there was some applied maths, there was some statistics, and we'd done all sorts of different things. It was an interesting course. And this particular question that I came upon that day was something along the lines of the following. I didn't take a copy. You can't take the paper with you when you go. But the question was something like, a tennis ball is thrown at a speed of 10 meters per second at an angle of 60 degrees to the horizontal towards the roof of a house nearby, 5 meters away and 8 meters in height. Derive the trajectory of the ball and comment on the result. So I saw this question, I was like, oh, I know what to do here, and the equations of motion and gravity and stuff. So I started writing down the formulae and started, deriving. And I remembered from revision that the trajectory, the shape of the path of the ball was going to be a parabola. So I could already see in my mind's eye what was going to happen here. And so I started drawing a picture to capture all the numbers that I've been given in this exam question. So I drew a person 5 meters away from a house, and I drew the house 8 meters tall, and I put a roof on it and so on, and then plotted out the parabola that I derived with the equations. And I could see at a certain point drawing this graph, I could see that the ball was gonna actually go over the house and land on the other side. And I thought, wow, that's so cool. I now know just from what they told me what's going to happen. And before I knew it, I was so happy with this. Before I knew it, I'd drawn a door on the house and some windows and the ball coming all the way over. And just at that moment, I was really happy to have made this little toy house and understood what was going to happen in that physical situation. And then I'd been able to write down the formula and figure it all out. And it was just so immensely satisfying. And I remember just sitting there in the exam hall thinking, this is cool.
I have to say, so thank you. That's, I think all of us can relate. You probably already had that exam and had the same experience with drawing the house and your parabola, which I don't even know what that is, but you can explain that another time. So I think everyone's like, yeah, we know how that is. But the thing that I was going to say is I was just reading a children's story, and they were talking about joy, and the little child was looking to look for joy, and the mother explained joy as a whoosh. So it sounds like you had a real whoosh.
Yeah, I did. I had a whoosh. And in fact, it was a similar whoosh to the one that I had in my hobby at the time, which was making models. I used to make, these model kits of aircraft, or more recently at that age, I started making my own models. Technology class at secondary school, we had a teacher that was, if I'm honest, a little bit lazy, and they just kind of let us do whatever we wanted. And so I used to, design pencil cases and cushions in the shape of globes and all these things that were somehow models. And that was the thing that gave me the whoosh. I would, design it and make it, and they'd be like, there was the thing. And I was like, oh, look, I've made an aircraft. And it was a little whoosh every time. So in that exam room, it was the first time I really had the whoosh of making a model out of math. And, I'd had so much fun in math all the way along through the course. And now here I was at crunch time, and they'd given me this amazing problem where I got to make a model, do my hobby in the exam.
Right. How many of you can relate to that whoosh? For those who you don't have your cameras on, for those who you do, have you had, even if it wasn't in math, have you all had a whoosh? A whoosh in your life? Yeah, I hope so. Somewhere along the line, a whoosh came along.
I hope people had a whoosh today. I don't know about you.
Yeah. Somewhere along the line. Thank you, Phil. That's great. I love thinking of you in that classroom in your math second level, having that whoosh. That's a great image. I can see you in my mind's eye. So with that initial whoosh, I want to ask you, how has that love affair, that whoosh, evolved over time? And if we're going to talk about time, could you just explain time to us briefly?
Sure, I can give you the physicist version of time, or rather, actually, no, the cosmologist version of time, because it's a bit simpler, it turns out. So the physicist view of time is that it's a dimension that we move through, just like this one and this one and this one. It makes sense, it turns out, to think of time as a dimension that you move through. It's the easiest dimension to move through because you can just sit here and there we go, I'm moving through time with no effort on my part. But it turns out it's important to think of it in that way, because when you get close to a black hole, I don't know if you were planning on doing this, but if you were to ever get close to a black hole, it would really matter that you think of it as in this way, because there the spatial dimensions and the time dimension get mixed up in a weird and completely incomprehensible way, unless you have the formula that allow you to predict the tennis ball and so on. And so you have to do it in that situation, and I think it's helpful in other situations as well. In cosmology, it's useful to think of time in this way, because in cosmology, which is the study of the universe as a whole, so not just all the galaxies and stuff within the universe, but everything, how it behaves together, on those largest scales, it turns out there's something that we call cosmic time, which is to say it's the time that everybody agrees on, no matter where you are in the universe. And it's defined, roughly speaking, by how hot the universe is at the moment. So there was a hot Big Bang 14 billion years ago, and ever since then the universe has been expanding, and as it's expanded, it's cooled. And it turns out you can measure the temperature of the universe as it is today. It's about 3 degrees above absolute zero. Space is pretty cold, but it's not absolutely cold. And so amazingly, because of the way the universe is so smooth, homogeneous, regular, we in our little galaxy measure a temperature of 3 Kelvin, and all the other observers in all the other galaxies will agree with us that at this point in time, the temperature of the universe is 3 Kelvin. So there really is a cosmic clock that you can rely on, and everybody can agree on. And cosmologists find this concept very comforting. It's one way of reminding ourselves how uniform and well behaved the universe is, and it makes calculations very easy to just have one cosmic time. And so we are all, on our individual galaxies, we're all moving through cosmic time at the same rate, all happily agreeing on the temperature that we see in the night sky. And so that's how, as cosmologists, we get to think about time. It's as easy in cosmology as it is in everyday life.
You all got that, right? So when the test comes later, you'll be able to answer that question. I trust you all. So given the breadth of your knowledge and what you've come to know, I'm going to go back again and say, so in the whoosh of that classroom back in 1994 to what you just shared with us now, can you say a little bit, I'm going to use love affair because we're talking about love, how has that evolved for you as to that you can talk about the 3 degrees, and we all agree on that. And, and all of that we've come to some understanding of, like, for you, when you think back to that moment in time, to this moment in time, to say what you just said, if you can just kind of say, like, how, I'll use love affair, but you can choose your frame of reference you want to say what that evolution for you has been like, of your understanding and where it's taken you.
Absolutely. Yeah. The story from my world line, if you like, we're all on a world line, as physicists say, but on my world line, coming from that exam room to where I am today, well, what happened? I guess I was so enamored with this idea of mathematical models of reality, that you could make models of things in the universe and how they work, that I got really interested in physics. And had so much fun doing it in the last 2 years at school that I wanted to apply to university and do it. And so I showed up at university, keen to study physics. Didn't know what it meant really to study physics at university. Turns out that studying physics at university means you get given a problem sheet every week, or 2 or 3 problem sheets every week, and you get to work through them using the material that you learned in the lectures. And the problem sheets are like puzzles to solve. They're brilliant. It was like doing that exam question 24 times a week for half the year. It was.
Some of us would think that's fun, but we're glad you did.
Well, I mean, if you like to spend your day, doing the crossword puzzle or jigsaw puzzles or anything like that, imagine what it's like to be a student where that's all that's asked of you, is to do puzzles the whole time. It was amazing. And so I did that. And then when I got to the end of 4 years of puzzle solving at university, we'd all got really good at puzzling by that point. And then the question came up, well, what to do next? And so I applied to do a PhD. And they asked me in the PhD interview, I remember this in Edinburgh, they asked me, why do you want to do a PhD? And I said, I just really like doing physics problems. I just want to do more. And of course, the people that were interviewing me, they're just like me. They're just big kids that want to do physics puzzles all the time. And so I got an offer from them to do a PhD. I didn't actually go there. I ended up staying in Cambridge to do the PhD, but it was the same. It was the same everywhere. All the physicists I met were the same. We're just big kids excited about doing puzzles about, describing the universe with math. So that was the, I guess, the story of me ending up in a PhD program. The big difference doing a PhD, so research in physics rather than being a college student in physics, is that the puzzles don't have answers anymore. So, when you're doing a jigsaw puzzle, you get a picture on the box and you put it up in front of you and you kind of use that to solve the puzzle. Well, imagine doing jigsaw puzzles where there's no answer. You just have to figure it out as you go. And so there, as a PhD student, I got into learning how to solve these much harder puzzles where we don't know the answer. But there are ways of solving the puzzles of the universe that allow us to have, confidence that we have actually got the right answer, that we have actually solved the puzzle. And so that was pretty daunting at first. And I missed having the answer in the back of the book, or the answer, the answer to the problem sheet at the end of the week. But what happened was I got quite interested in part of the puzzling method, which is how to actually measure things. So it turns out that the models that we make of things in the universe as physicists, they're different from models that other humans make in their day-to-day lives. And everyone's doing it, by the way. Everyone's representing the universe somehow. They're either, writing stories about it, or telling jokes to each other about it, or they're painting pictures of it.
Eating French fries.
Eating French fries, yeah. I mean, that reading that you did at the beginning, Alyson, was a fantastic example of somebody using wonderful language to somehow represent the universe to the reader. And it wasn't an accurate depiction of the universe, but you could sure tell what they were trying to say. My literal mind was saying, well, hang on, the universe didn't begin as a block of ice, blah, blah, blah. But if I take the literal physicist hat off, it's a beautiful depiction of how structure in the universe evolved, and it's like this and not like that, and so on. And then it gives you the impression of what's going on, even to the point of the end being an observer in the universe and eating French fries. So, but the difference is that the kinds of models that we make as physicists are scale models. So remember I said I used to do airfix kits of making model airplanes. Those are scale models, and I think as a kid I already found that very satisfying. That the model that you ended up with really did look like a plane, and the wheels were the right size compared to the plane, and it had the right stickers on it as you would see on a real plane, and it was a very accurate depiction of reality. It was a scale model. Now impressionist paintings are very far from being scale models. Dali-esque paintings even further, but they're still models. But the physicist models differ in this key respect. They're scale models. So what does it take to make a scale model of something? I mean, if you imagine making a scale model of your own house or apartment, maybe you're going to give it to a friend as a toy, you would have to do a whole lot of measuring, right? You'd have to go around with the tape measure and you're like, how big is this room? How tall is the ceiling? Because you'd want it to be, the fun part would be making it a scale model of your actual place. And so for physicists, the measuring part is very important. Like, we have to get the measurements right in order to be able to make a scale model of the galaxy that we're studying, or the planet, or the universe as a whole, because it's having those measurements, getting the scale right, is what allows us to make accurate predictions of what will happen next, or give us an accurate understanding of how things work. Because if you don't have the pieces in the right size relative to each other, then then you might make mistakes in understanding how things work. And so for some reason, I'm not quite sure why, I got interested in this process of measurement. How do you actually measure things in the universe? You know, going around your apartment with a measuring stick sounds easy, and it is. But there is, you know, when you look at it, the problem in great detail, and set yourself the ridiculous task of measuring your apartment with extreme accuracy, then it becomes quite a hard problem, because it starts to matter how straight your measuring stick is, and it matters whether you've put it down in the right way every time. And you end up doing things like measuring it 10 times and averaging the measurements together, or you get, you know, 3 different measuring devices and measure it with all 3, and then you compare the results and so on. And it's the same when we're trying to do things out in outer space. It's harder, of course, because we can't go there with a measuring stick. We have to find new ways of measuring things in the universe. But the problem is basically the same, that if you want a really accurate measurement, then you have to do things multiple times. You have to cope with the fact that your measurements are uncertain. And that coping with uncertainty and avoiding making mistakes is really what statistics is all about. And statistical inference is what I got interested in, the process of measuring things accurately.
This isn't the next question, but as you're saying that, it makes me think of, as a faith community, and so I'm just going to use the word theology, which, you know, we could stick in a lot of other words of, I'm thinking about the ways these two things kind of relate to each other, of, you know, measuring one sense of what does it mean to be on a faith journey, and how do you measure that, and what do you use, you know, what are the measuring sticks you use, and, you know, is the intent to be accurate, or is it the intent to just be in this place of discovery about that? So I'm struck by, from where you started, of having your people in your house and your window and the ball going over, to coming to a place of being okay in the not knowing, and being excited about the not knowing, and having enough tools to kind of work within the not knowing that still gives you the satisfaction of puzzling, that still gives you, and moves the thinking forward, moves the understanding forward, even that you're still kind of in the space of a not knowing, you know, kind of exactly where it's all going to go.
Yeah. And it's funny, I do feel some resilience in myself that maybe I've developed through studying the measurement process. And this, in particular, coping with uncertainty, you know, recognizing that none of the measurements I make are ever going to be absolutely precise or accurate, and but that as long as I have a process for dealing with that, and coping with that uncertainty, thinking in terms of probabilities rather than absolutes, has actually, I think, been helpful for coping with all sorts of situations in life, because I've done enough of it now at work that I kind of get probability, and I'm comfortable with the sense that, yeah, it's probably like this, but maybe it's like that, and so yeah, I'll do a bit of contingency planning in case it's like that, but it's probably like that, so I'm probably okay, so I'll keep an even keel on that. So I recommend it. Get into statistical inference, understand probability, and feel more
We'll
secure.
save that for next year. We'll invite you back to talk about that.
Yes.
So I'm going to move us forward, and the next question that all the guests have been asked to reflect on is, and you may have kind of shared some of this in what you've been telling us about in the kind of evolution of things, of something that's been most joyful and meaningful for you in your career. And Vanessa and I are using the language of what made your heart sing, or the whoosh, but you can kind of pick whatever you want if you have some examples of, you know, in that evolution, kind of where those moments of where the whoosh, the joy, the meaning really has rung out for you.
Yeah.
The bell.
Yeah, I mean, this is another great question, because, you know, if you, when you started out, you're asking, where have you found joy and meaning? And it's kind of hard to answer. And then you come back to asking, well, where did you feel the whoosh? And I know exactly when I felt the whoosh.
It's a body thing.
Exactly. Yeah. So, there's been many. Let's see. Okay. So I spent a very happy train journey coming back from Bologna in Italy to Oxford in the time when I was living and working in Oxford. That was just before I moved back to California this last time. I was traveling by train a lot then because I was trying to avoid flying for the environment. And then I found that train journeys are actually really fun. And so on that way back from Bologna, I'd been kind of thinking about this problem for the few days before when I was on the visit there. And then I knew I had this long train journey. And so I sat for maybe 6 or 7 hours straight with my laptop. And I turned all the ideas that I'd had in the previous few days about how to make a particular model. I sat down and I wrote out the math of the model. And then I wrote the computer program that took the math and turned it into a computer model that can then take in an enormous amount of data and make sense of it, and then give out useful answers for a particular measurement. And the model I was making was also especially fun because in this instance, it wasn't a model of, a galaxy or the kind of thing that I usually study. It was actually a model of a crowd of people who had been helping with understanding 30,000 images of galaxies. So to back up a bit, what we did was we got 30,000 images of galaxies, and some of them, we didn't know which, some of them were gravitational lenses, and we were trying to find the gravitational lenses. Gravitational lens is where you have a massive galaxy with a far off in the distance behind it some little faint blue galaxy. And if the faint blue galaxy is right behind the massive one, it's not that you can't see it, it's that the light comes round the massive galaxy and towards you, and then the path gets bent around the massive galaxy. That's gravitational lensing. Anyway, what it looks like in the image is a big yellow blob. That's the massive galaxy in the foreground, and then a blue ring, or maybe a set of arcs arranged around this massive yellow galaxy. And those arcs are distorted images of the background thing, but they've been magnified by this gravitational lensing effect. So it's an amazing thing when you see it, that the universe really does this. And they turn out to be useful for all sorts of things, including weighing galaxies, like making a measurement of the mass of that yellow galaxy. And so we wanted to find more of these things. The problem is how to do that. And at the time, it was quite difficult to teach computers to recognize them. And so what we did was we got 30,000 images of things that could be lenses, or were at least known to be massive galaxies. And we just showed them via a website to 10,000 people. And they spent their lunch times like clicking through these images saying, nope, not a lens, nope, no, no, no. Yes, that might be a lens, no, 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 no. And so each person did, well, a variable number. Some people did hundreds, some people just did a few. And the problem I had was how to make sense of all of these votes, because these people were, they were doing this classification task, but we didn't know how reliable they were. We didn't know how good they were at spotting lenses. We'd given them a tutorial, but who knows how much they understood of it. And so we had this very kind of uncertain, noisy data set, a whole bunch of votes from a whole bunch of people we'd never met, and had to make sense of that. And so the thing I wrote on the train was a little model of this crowd of people and how they work. And it was a very simple model. We just said, each person has some talent for spotting lenses. We don't know what it is, but we'll try and estimate it from what they've done. And then we'll combine all of their answers together, and we'll then look image by image and see what they said. And it turned out to work pretty well. The fun thing was that the way the math works out is that it doesn't matter how good you are at doing this task, how good you are at spotting lenses. It just matters that you're consistent. So if you're consistently bad, that's also informative, because because my model knew that they were consistently bad and would take that into account. And so that was hugely satisfying. That's why I was so excited to do it on this train journey, because I realized that everybody's input was going to count. Like, it didn't matter that if they'd done it badly, everybody's input was going to count, and this model was going to capture it all. And so I knew that going into it. And so I just sat there on the train, whooshing along. And it was great. That was one of the most fun things I think I've ever done at work.
Yeah, it makes me want to have you do a model of that for church. That everyone does something consistently, even if we don't do it perfectly, to reach towards that thing of like, we have a greater understanding. I mean, is that kind of what we do anyway?
Yeah. It's funny, these agent-based models, they're used all over the place. They're used to understand traffic, pretending that drivers are reliable, rational people, but then throwing some uncertainty in and seeing what happens. And they can, they can work extremely well.
So we have about 10 minutes before we're going to open it to Q&A. There are 2 more questions. So we've gotten to hear, with your great stories and imagining you on your train and in your classroom and, all the places that you got to get to kind of engage and immerse yourself. And I want to know, what's been the most challenging for you? What have you learned from that challenge?
Yeah. So let's see. I mean, as I progressed along my world line, learning more about the puzzling process, the measure how to make measurements and so on. What happened was the field around me was changing as well, and that to get at the big questions in cosmology about what the universe is doing and why, turns out to answer those and with ever more accurate measurements takes more and more data and also more and more people to do it. And so right now I'm working on a giant survey telescope that's going to spend 10 years observing the sky and build up a huge data set, petabytes, not gigabytes or terabytes, but petabytes. And then hundreds of people will use it in multiple different ways to try and make very accurate measurements of what the universe is doing, in order to try and understand, well, first make accurate measurements of how fast the universe's expansion is accelerating, and then after that figure out why it's doing that. I don't know, Alyson, did you know that the universe was expanding at an accelerating rate?
You told me that once, and so I just keep telling everybody else, because that's what you said.
It's an amazing thing. You would think that, after the Big Bang, the universe expands and it would slow down under gravity and then collapse back in, right? What goes up must come down. Turns out that the universe doesn't do that. It's just getting faster and faster and faster, and nobody knows why. But it turns out that to really get, at this point, to get at why that's happening, to make very accurate measurements of that phenomenon, and then afterwards understand why it's happening, takes a huge amount of data and a very large number of people to do it. So this is big science. And the mathematical modeling, the coding and stuff, I would say was relatively straightforward compared to the cat herding problem of getting a large group of people together to all work in concert to make the same accurate measurement.
We use that cat herding thing when we talk about church too. Interesting.
So working in larger and larger collaborations and figuring out how to make those work, I would say that's been perhaps the most challenging thing, and has led me into all sorts of places that I wasn't expecting to go, like management training and thinking about diversity, equity, and inclusion, and really having to think hard about what a group of people needs in order to be successful at a particular task. And so it's still all the same. There's still all the same problem, solving the puzzle of why the universe is accelerating. But the particular techniques that I'm now working on are quite different from the ones that I would have imagined as a PhD student, for example.
Yeah, well, there's many questions, and I'm sure other people are like, oh, I want to ask about something like that. So if you're thinking questions that go back to anything, keep them on a piece of paper, or put them in your back pocket or somewhere, is this imaging work that you're doing right now with all these images that you're collecting in the sky, to know, like, and I don't know the answer to this, maybe you do, of like, in the time of in your lifetime, to collect all that data, analyze that data with the intent of giving it over to people you don't even know yet, who will take it wherever it's supposed to go. Like, I'm sure you think about that. Or tell me, do you think about that?
Oh, we do. I mean, one of the reasons why I think I was drawn to this particular project is because it does have this ethos. This is Rubin Observatory we're talking about here. Rubin has this ethos of the survey that it's doing. The name of the survey is the LSST. It has this ethos that the LSST is for everyone, and that we're surveying the sky, we're building this data set, and we really want it to be used by as many people as possible. And not only astronomers, using it in many different ways to measure all aspects of the universe on many different scales, but also we want it to find its way into the hands of people beyond professional science, who can use it to further their own understanding of the universe, and feed their own excitement about what's going on out there. Because it turns out that we all have the same big questions. Everybody loves the night sky. Everyone has feelings of one sort or another about the great unknown. And it's something that not only we can bond together over, it's something that I think really speaks to some quite fundamental inbuilt drives that we have to explore and also to cooperate. And I think there's a lot of a huge amount of value that humanity can get from this survey and having access to the night sky, to the deep night sky in the way that we'll enable. And that's a whoosh.
Yeah, that is a whoosh for sure. We've gone over a few minutes into our letting you answer questions that we've come up, and now we're going to open it up, if that's okay. So I just have to say, Phil, thank you for sharing your story. And given where we just landed, to thinking of you back in that classroom, coming up with your model, what an amazing journey you have had, and how lucky we are to have you in our community to share that with us and to enrich our lives in your story. So thank you. So I'm going to open it up now. You can either post a question in the chat if you'd like, or you can unmute and maybe raise your hand just in case there's a few people who want to ask and I can call on you. Come on, people. What's that burning question you've been dying to ask, Phil? Margaret.
Thanks. Thank you very much, Phil. I hope I can articulate this, but I like to go to the planetarium, and they're reopened now, and I watch their new program. But while I was watching it, and he was saying all these things, we talk about time, but what about, it seems to me that there's distance. When these things are so far away, is it realistic? I mean, if we're seeing light that was kind of left the place before the world even existed, I mean, is that so far away that you can't even really, that it's, it isn't realistic to think that you could ever really know it? I don't know. Does that make sense at all, Phil? Or do you understand what I'm saying?
I do, absolutely. The distances are enormous, and it has an important consequence for how we think about observations of the universe. The trick is to think of the deep night sky like an archaeologist or a paleontologist. So what they do is, the paleontologists, they'll dig down through the earth, right? And the further down they go, the further back in time they get to look, right? Because over time the layers get built up. So so there's dinosaur fossils from 100 million years ago here, and then you dig a bit deeper and you get to 500 million years, and you're going back in time by digging down. So it's the same in astronomy, that the further out you look, the fainter you go, the further out into the universe you look, you're seeing things as they were a longer time ago because of all the time it takes for the light to get to us. So we might see a galaxy here halfway across the universe. We're not seeing it as it is now. We're seeing it as it was 7 billion years ago. Mm-hmm. And so we can't know it now. We don't know what's happened to it in the meantime. What we get to see is the archaeological record of that galaxy. And it turns out that that's plenty to understand how galaxies work in general and how the universe behaves overall. We won't ever get to see that galaxy as it is now, but that's okay. It's telling us how the universe was then, which is kind of an amazing thing if you think about it. It's amazing that paleontologists can look back into the Earth's history by digging down. It's amazing that we can study the universe's history just by looking up.
Beautiful. Thank you. Margaret, did that give you did that help? Did that help?
I can see that, but as far as say traveling, using, going to other planets or doing something, I mean, the traveling aspect of how is this going to be useful to humans, or, how are we going to escape global warming by this, and the time and the travel, it just, I can't get them to match as, but I'm glad somebody's working on it.
Keep working on it, Phil.
Yes.
I'm gonna just hit pause there for Margaret because I know Athena's got a question and I want to make room for other people if that's okay, Margaret. Athena, go ahead.
Okay, thanks, Alyson. I've so enjoyed this wonderful talk that Phil's given. And just this last answer though, that if you look at a galaxy and it's 7 billion years old, that just blows my mind. So say that. But I just want to ask you then, with this ever expanding, faster universe, I have read and maybe watched a YouTube video or two about this speed of light maybe not being a constant, or there are different measurements around that. And I'm wondering, is that true or not? Or are there just different ways of understanding that idea?
Yeah, I mean, it's we've known for, I guess, over 100 years now that the speed of light really does seem to be a constant. And, this is an amazing thing on its own, that the universe is like this. But of course, we shouldn't take no for an answer. We should keep questioning it. And so there are people who are actively looking for tiny changes in the speed of light. For example, as the universe has evolved, it's a valid question to ask. Is the speed of light in the universe now the same as it was, let's say, 7 billion years ago? And there are, astronomers who are trying to answer that question by making extremely accurate measurements of galaxies 7 billion years ago, the light from galaxies emitted 7 billion years ago. So far, there hasn't been seen any evidence that the speed of light is different now than it was then. But that's not to say that small differences won't be found. And if they do find them, then it will be a puzzle to figure out, why has it changed? What's the universe doing? And so I think it's a great investigation to do. It's a great measurement to try and make. And it's amazing either way. I mean, why should the speed of light be constant? Everything else seems to change in the universe. Why should the speed of light be the same? But that's the way it seems to be.
Thank you. Thanks.
Okay, go impress people at your next cocktail party with that answer, Athena.
I will. Thanks.
Tom?
Yeah, thank you, Phil. This is absolutely wonderful. So I have a question about looking at the night sky and the stars. When I look up, I have a really, really hard time seeing three-dimensionally. I look at Orion's belt and I see 3 stars, and I know that they're not in a straight line. But even knowing that, staring at it, I can't do that. So my question, are you able to do that?
Nope. In fact, there's a running joke in astronomy, or at least there is the astronomers that I knew in Cambridge. There was a running joke that, the difference between small and far away, small, far away. I mean, it's just very, very hard to tell. And it's the same when we're studying galaxies, just as it is when you look up and see the stars. It's just hard to tell. It's hard to see in 3D in outer space. And in fact, we put a lot of effort into trying to measure the actual distance to things, to galaxies, for example, or to stars. It's a really hard problem, hard measurement problem, and it takes a lot of hard work to do it well. And so everyone's in the same boat, whether you're looking up at the night sky or you're trying to use big telescopes to measure the distance to galaxies. It's just hard. It's basically, it's our lot in life. As Margaret was saying, we can't go to these places. We can barely get to Mars. We haven't even got there yet. Getting to another star, maybe one day, but everything else is just too far away to even think of going there. Other galaxies, forget it. And so we are here on our little blue boat, and we get to look up and try and make sense of the night sky as best we can. And the professional astronomers have just the same challenge as you do.
Doesn't that make you feel better, Tom?
Yep, it does. It does.
In a weird, I wish I really could know. So we've got a couple minutes. Is anybody else? Don, you got your finger up, hand up? Yep. And just you're muted, just so you know.
Athena, was this a new question?
No, I don't know how to put that hand down. Yeah. Lower a hand. There we go. Thanks.
Yeah. I'm a mystic in my sense of a place in the world and understanding, which might be what you said about probability sort of fits into that, But and so I have this sense of wonder, what is it all about, which is you've been addressing, specifically making a model of what it's about. But can you talk about a sense of wonder that you have at all, or if I'm remembering what I read about what Einstein said, he didn't believe in any force in cosmology. He said, but there still has to be something there to explain it. If I have it right, is that? Do you have a sense of? Yeah, can you talk about that? Yeah.
I mean, the sense of wonder that I personally feel tends to come in small shots, little whooshes. I mean, I mentioned seeing a gravitational lens, and it's amazing that the universe does that. Seeing the latest plot that shows from the measurement of distances to supernovae compared to their apparent recession speeds that allow us to understand the local expansion rate of the universe. Just to see that, and to see that yes, the universe expansion really is accelerating, and remembering, what's up no longer comes down. It's amazing. That's the sense of wonder that I have, that the universe is doing these amazing things, and some of them we understand and some of them we don't. And I think one thing that really got me a few years ago, and I like to pass on to people, and it's connected to this sense of wonder and a search for meaning, is that cosmologists, for much of our practical life at work, it suits us to imagine that we are outside the universe, thinking about our model for the universe that we might, set upon a desktop and study. It's important to, from time to time at least, remember that we are not actually like that. Yes, we're outside our model of the universe, but actually we're inside the real universe. And so as constituents of the universe, as parts of the universe, what we're doing is something, I think, which is truly amazing, which is we are in the universe, representing the universe through our models, representing the universe back to itself. So Richard Holloway likes to talk about this. He said it's taken it 14 billion years, but now we have we are beings in the universe that are the universe asking questions of itself. Like, we are the ones who are searching for meaning. We are the universe searching for its own meaning. And that sense of being part of the universe as the universe tries to understand itself through us that certainly got me when I first heard it. There was a little whoosh right there. And it's something that I think is useful for anybody who is wondering about meaning, that we are, because we're part of the universe, we can think of ourselves as one way in which the universe is trying to understand itself.
I'm gonna thank Don for his question, and I'm glad you got Richard Holloway in there, because I love when you told me that story. It's I love thinking about eating French fries and thinking about that. That totally makes my day. Our last question is going to come from Merle.
Yes, I want to go back to Margaret's point, a question that you didn't get to answer after that, and see if you can talk about how you see this as relevant to the problems of our current time.
Yeah, absolutely. So I think there's a lot of relevance, actually, but it's not direct in the way that that we might like it to be, but I think nonetheless it's important. So, right now we're in a pickle, and it's clear that one of the ways out of the pickle is in applying science to help ourselves. Understanding the state of the world, the problem of climate change, how to cope with it, how we're going to work together to get through this. That I'd say the problem is maybe not as bad as it was a few years ago, but there's a real problem with getting everybody on board and together and cooperating and believing in science and taking appropriate action and really tackling the problem in a way that we need everybody to. And so where does astronomy come in? Well, a number of ways. I think astronomy is very interesting to me from a social point of view, because all of us are somehow united by an appreciation of the night sky. It's the nearest frontier to us, right? You can look up at the night sky and wonder about it, and you're probably close to asking a research question, right? We just had one just now about the speed of light. It doesn't take very much to get to a research question looking at the night sky, and all of us can do it, right? No matter what your political position is or your background or whatever, we're all able to understand the mysteries and the scientific approach to those mysteries of the night sky. And so it's a gateway to better appreciation of science. That's one way in which it can help. Another way is that you might wonder, well, why are these scientists spending their time studying cosmology? Why do that? Why isn't everybody being redirected to the World War scale problem of tackling climate change? It's a question I ask myself. Like, why did I carry on in cosmology and not jump ship and go work in climate science or any of these fields that are more applied and lead to direct solutions that will be of practical help? And what stopped me from doing that was a conversation with my mentor at the time, and I wondered out loud to him about this. And he said to me, that with climate change and other things going on in the world, but especially climate change, that it was going to be tough. It was going to be a huge challenge for everybody on Earth to tackle this. And it was going to get a whole lot worse before it would get better. And all along that process, people would need hope. They would need to feel the progress that humanity was making in other areas, even while it was really struggling to get past climate change. And I thought about this, and I think he's right that if all we do is just try and solve practical problems to do with mitigating and coping with and adapting to climate change, we will miss something important, which is the sense of progress that comes from following sciences like astronomy, where discoveries are made for their own sake. You know, if you pick up the newspaper and look at the back page and see, you know, the latest discovery about how black holes work or some new thing in the night sky, and it's amazing. It transports you away from what you've been worrying about, and it reminds you that we are a species with enormous potential for exploration and discovery, and that if we can do this, understanding the universe, then we can do anything. And I think that hope is important.
Yeah. Thank you, Phil. I mean, it's a big question, and I appreciate you being willing to take it, and I appreciate your answer. I think the hope is critical, to just know that, you know, we are part of this expanding universe, and so to understand it helps us live in the times we're in, hopefully. So here's your last question, Phil. You've been waiting for this one, and this will be our wrap-up question. So here it is. What magic, purpose, or superpower have you gained through your work? How do you want to share that magic or superpower or purpose with others? And you shared some of that, but if there's anything else particular you'd like to say about that.
Okay, so remember I said that the biggest challenge was working with the big collaborations and the herding of cats and the getting big groups of people to do difficult, complicated things together. And so I think, I mean, I'm not sure I'd really call it a superpower, but let's, for the sake of this question, let's call it a superpower. The superpower is one that I think I've developed from trying to solve that problem and looking at what works and what doesn't. And the superpower is I only ever try and say positive things. And that turns out to be, I think, the single most important thing for working with a big group of people, trying to cooperate, trying to do difficult things. You know, just try and turn whatever piece of negativity may have cropped up into something positive and keep moving. It's this question of hope, but also how to really truly cooperate and connect. Is just keep looking for the positive and keep focused on that, and everything else just kind of comes along with it.
Well, you've been a positive force in our lives tonight. We're so grateful for you, and thank you for making time for us, for sharing your love with us, and inspiring us to look up at the night sky and to see ourselves in it. So thank you, everyone. You can go watch figure skating now if that's what you want to go do. Have a great evening. It was lovely to spend this hour with you. Take care. Thank you, Phil. Big hearts.
Thank you, everybody. Great to see you all.
Yeah.
Thank you.
Thank you. Thank you
so much. Good night. It was great.
You're welcome. It was great to be with you all.